Hi, thanks very much for introduction. I realized it's a very ambitious task to talk about biosecurity and climate in 5 minutes, but I promise to take you from Canterbury to Antarctica and let's see what happens. Okay, so those basically both topics are part of NIWA project, which is a data platform funded by MB. And here we aim to create a data platform for environmental data science in New Zealand. One of the research tasks I'm interested in particular is anomaly prediction. And anomaly prediction can be used in various areas, such as climate and biosecurity. And what do they have in common, both those topics? I will start with biosecurity. So for the biosecurity, our task was basically to try to find invasive species before they get established in New Zealand. And for this, we look at trees. There was a presentation before by Richard Green who talked a lot about trees, and the same area I will also discuss trees, in particular in Christchurch. So we focused on Christchurch as one example, and what we actually decided to do, we decided to find out whether we have unseasonal changes in foliage, which can actually tell us that possibly we have invasive species such as Dutch elm disease, which is carried by beetle. And this was our goal, and for this goal, the first task that we decided to do is basically start with looking at trees and trying to segment them, for which we had to hire some PhD students, actually forestry students, and create a data set. Surprisingly, it's really hard to do, so for a human it takes several minutes per image to annotate, which you can see on the right-hand side here. To pick up this beautiful cabbage tree requires quite a bit of time. After this data set was built, we applied deep learning model to find actually whether we can segment trees for several species which we decided beforehand. And I'm gonna show you some of the results. So basically, it was, the first part was quite successful, and indeed we could find on the streets where our trees are. So the next part actually is gonna be to run a rubbish truck with camera on top and create a data set and find anomalies. And this was preliminary work for this ambitious task of anomaly detection on urban streets, which was done by one of students for Data 601, which is a capstone project for applied data science. What if we decided to move from urban environment to Antarctica? What is going to happen there? Well, basically, we still can have anomalies, and the way it's related to Canterbury, where our trees were located, in Antarctica, we have a condition which is called fern winds. So in Canterbury, if you've ever been to Christchurch, you might experience unseasonal hot wind. And surprisingly, we can see this, if you go to Antarctica, we can actually experience it in Antarctica as well. And the idea is it's anomaly because it's a rare event. And how can we basically find out when it happens? If you look at the data. So that was a project done by PhD student Tobias Mills. And for this, we applied also deep learning for area of Antarctica, which is called dry valleys. And the idea was we can use the first generative AI, which was designed ages ago, which is autoencoder. And in this autoencoder, we can generate actually normal days without any anomalies. And here we are looking at time series for temperature together with winds and atmospheric pressure. And we can find, if we can generate normal days, which is, our error is going to be quite low, but for anomalies, our error is going to be quite large because we don't have many examples. And this is the core idea which we use to detect whether we have fern wind conditions from the data coming from our weather stations. And this actually talk is gonna, well, this research is gonna be published soon, so please watch the space, and thanks very much.
So Harvest Hub is a spin-off from the Nelson AI Institute. And Nelson AI, what it seeks to do is to find problems in the environment that we might be able to address using AI and investigate these problems, do a bit of R&D, and then potentially spin off a venture to turn that into a product and really make progress with that. And Harvest Hub is one of these spin-offs, and Chris is the lead ML engineer there, and so this is his slide deck. And it's all about the aquaculture industry. We believe that aquaculture is a very sustainable source of protein. Some data Chris has put here indicates, the productivity in terms of dollar value per hectare for these different products, and you can see that mussels and oysters, they're nowhere close to as valuable as salmon per hectare, but they are much more valuable than many of our other industries on the basis of area. And of course, we have a lot of ocean space to do that. So Harvest Hub is all about optimizing yield in aquaculture, particularly for mussels. And the current way of doing it is very much manual. So people go out on a boat, they pick up some mussels, they look at the mussels, and they come up with a thing called a condition score, which gives them guidance as to whether or not they should harvest those mussels. And the accuracy of this is unknown. So this mussel here has a condition of 7, which is quite good, and it's probably ready for harvest. But it's actually hard to tell this by eye. So what we've done here is taken this problem and thought about how could we improve it, because harvesting at the wrong time can be an expensive mistake. And so we can really improve yield here by optimizing this harvest. And so what we do is we've built a smartphone app, which actually you're going to hear about in the talk later. But the smartphone app is used to take photos of mussels on a boat. And then we have a process whereby we segment the mussel and we pass the image to a deep neural network, which we've trained. It's based on this ConvNext V2 architecture, which is a CNN approach. And we estimate the cooked mussel weight, which is kind of the final measurement of yield. And this tells us how sort of ripe that mussel is, if you like, how close it is to being ready for harvest. And so what we've done is we've done an initial data collect, and we've trained a model, and we've got some initial results. It's very early days, but the results are shown here. This is just a prediction error, which it's 90% of our estimates are within plus or minus 39% of the actual cooked weight, which from a smartphone image of a mussel, we think it's okay, it's a good start. Now, this column here in the middle, the harvest decision accuracy, this is where it gets really important. This is about whether or not you would have made the decision to harvest those mussels. And in this case, our model is producing a number which is better than the current way of doing it by eye. Now, in the final column here is if you rank your mussels by cooked meat weight, which is the kind of ground truth metric, and then you compute the spearman's rank correlation, you can see that our model outputs are much more closely correlated to that than the subjective condition score. So this was from an initial data set. There were a lot of issues with that first data set that we used to build this model. The next step is really to use this mobile phone app that you'll hear about later in another talk to collect a lot more data, improve the model, and then deploy that model on a phone to help people out in the field on their boats. So with that, I'll wind up, and thank you.
Hello, my name is Sara, and I'm here to talk about the insight from some research that I have done to predict Auckland PM10 using LSTM and MLP, and in 5 minutes. So what is PM10? PM10 are particles that are suspended in air, and they are less than 10 microns in diameter. And the source of PM10 is human activities from biomass burning and some traffic. And Auckland is and it's the most cities, so you might think that we are benefiting from the clean airflow, but the sad news is that most of the natural resources contributing to PM10 concentration is from marine aerosols. And in each year, there are about 3,000 tons of PM10 that are emitted to Auckland's air, and there are days that PM10 concentration are exceeding air quality targets, and that's not good because it contributes to various health effects for vulnerable people like elderly, children, and people who have some existing health issues. And according to Auckland City Council, 1 in 4 children suffer from asthma in New Zealand, and there are around 260 premature deaths in Auckland because of the poor air quality. And you can see that in South Island, the rate goes higher. That's why it's important to monitor and try to predict and estimate PM10 concentration to control the air quality and make it more manageable and create a safeguard for public. And what I'm trying to do is to see how reliable and efficient are these two machine learning models, LSTM and MLP, for predicting hourly PM10 concentration, given that there are not much emission inventory information in Auckland, and the weather data that are being collected are quite limited. And these are the stations that are collecting PM10 data in Auckland Airshed, and I'm focusing on number 4, which is Penrose. Penrose is located on State Highway 1, and is nearby an industrial factory, and also surrounded by some residential areas as well. And the data was collected at, oh my God, at 1 hour resolution, and followed 2 guidelines. And data that I collected was trying to collect was PM10, NO, NO2, and there are co-pollutants and some meteorological data. And we pre-processed the data, trying to clean them, and the missing data were imputed using MIC, Miss Forest, and KNN, and the best method was found out to be the MIC Forest for imputation due to some statistical methods and graphical methods. We collected data, and I think I moved from this part, but the main data analysis was that the PM10 concentration in Penrose are from southwest, and you can see some variation in data, and you can see how NO2 and PM10 were going down during the level 4 lockdowns in 2020, 2021, and sometimes in 2022. And the models created 2 models of LMP and used LM propagation algorithm. We searched for the best parameters using grid search, and the best learning rate was 0.01, and the R-square was 0.65, which was not bad, well, moderate. And the second model, we introduced 2 hidden layers and tried to find the best combination of the nodes in those hidden layers. The best combination was 223 neurons in 2 hidden layers, and the result on the test set was better, about 73%, and created LSTM. And okay, they tried to optimize the LSTM method, introduce a new framework, and find the best epoch, then keep the epoch constant, and find the best byte size, keep those constant, find the best number of the neurons, and here's the final results. LSTM performed better than MLP, and as you can see from the graph, ignore the orange one because this is for another experiment. I was too lazy to repeat my experiment and to generate a new graph. But yeah, LSTM performed better, and MLP failed to get the prediction estimation when it was when we had a lower level of concentration, and LSTM was almost better when we had the spikes. That's it. Thank you.
Hello, thanks for having me. So my name's Gemma, and I'm a data scientist at NIWA, and I'm stationed here in Auckland. And we have a lot of data science applications at NIWA, but the one I wanted to talk to you about today was global weather forecasting. And the reason I wanted to tell you about global weather forecasting is that data-driven global weather methods, or weather models, have recently had some serious advances. So there's a whole list at the top of this slide of things that have been developed just in the past couple of years. And every time I give a talk on this internally to NIWA to tell them the state of the field, I have to tell them, so last week. And a really big milestone is this quote here from the European Centre for Medium Range Weather Forecasting, which is the ECMWF. They had a blog post back in June where they said that they themselves had looked at Pangu weather, which is one of these earliest really good data-driven global weather models, and they say it is a legitimate rival for the IFS. What is the IFS? It is a leading global numerical weather model out there, and in particular, who makes the IFS and runs it? ECMWF. This is the people who make the model saying, okay, yeah, you can compete. Fair enough. And in fact, ECMWF since then have already started making what they call the AIFS as a complementary model. And a bunch of other weather organizations around the world are also starting to try to make their own AI-based global weather models. And Google has a site they call Weatherbench where they compare on different metrics some of the models that are out there, not all of them. But if you look at that plot there, this is from Weatherbench, anything that's blue is better than the IFS. Anything that's red is worse than the IFS. The physical models are in blue up the top. The data-driven models are in that red box there. And you can see a lot of them are just beating it on every single point. They are actually better. And the really remarkable thing about this is not only are they giving more accurate results, they're faster. How much faster? Much, much faster. We had a whole talk about how AI is bad for the environment because it uses too much compute. In weather, it's the opposite. It is the non-AI that uses all of the compute. So a 10-day forecast would take, 10 to the 5 CPU cores for about an hour. Or you could do a minute on a GPU. And of course, that doesn't take training into account. Training time takes longer, but that's very exciting for us. So architectures they actually vary quite a bit. We've got graph neural nets, we've also got transformers. The really important thing here is that we've got things that can compare large-scale patterns across the globe so that you can predict what's going to happen by looking at large features. And one thing we're interested in NIWA is, are they any good over New Zealand, and are they any good at extreme weather events? Because statistically, you'd expect fewer extreme weather events. Can they do it? So I've been looking at Cyclone Gabrielle, at performance on that specific event. In line with other people's analyses of other extreme events overseas, they can do cyclones. They've seen plenty of cyclones. They are better than a standard weather model on Cyclone Gabrielle if you are looking at a global weather model. But be aware also that NIWA and many other national weather organizations around the globe, we don't run our own global weather models anyway. What we run are local weather models. So we do higher resolution over New Zealand. We've got the NZLAM and the NZCSM, which are 4 kilometre and 1.5 kilometre respectively, as opposed to these global weather models where you're looking at more like 30K. And so we can do better than this, zooming in. But then the question becomes, what does this mean for local weather forecasting? And the answer is we don't know. Global weather, you've got a new paper out every month, and it's doing some hot new thing. There's almost nothing on local area models at the moment. And that's a fascinating research direction, and we don't know where it's going to go. Maybe we use the same techniques on a smaller domain. Maybe we operate our own huge global model, but then just kind of zoom in on an area, which we can do now. Like, we wouldn't have the compute to do that for a numerical weather model, but for this, we could run a global model and also have the zoomed in area, and it wouldn't be anything worse, or we downscale, or maybe someday our global models will already be detailed enough. But that's a long way in the future. Who knows? Thanks for your attention.
Hey everyone, just imagine you're trying to build a cutting-edge AI solution, but what you're missing is a large, high-quality data set. So how do you gather this in a scalable way? Hi, I'm Dana Lambert, and I'm a software engineer from Harvest Hub. And today I'm going to talk to you about the solution and the challenges we faced in building a data collection for muscle condition. So hopefully this can provide you with some insight into your own data challenges. So as Julian mentioned before, who is Harvest Hub? Well, we're a startup out of Nelson AI Institute who is trying to solve environmental problems with AI solutions. So Harvest Hub is trying to solve the problem of objectively defining muscle condition with an AI solution. So first off, we needed data collection. So to get this, we needed lots of images, videos, and data and measurements of shucked muscles from various muscle lines. And, well, we had to get this from scratch, a large data set. So we thought, you know, we'd probably want lots of people involved in this. So when you've got lots of people involved in data collection, how do you make this standard? How do you make sure that people are collecting the right data for you? Furthermore, we needed to collect measurements as well as your photos and videos, and how do you keep all this data organized? Finally, because we've been out on a boat, we find ourselves without an internet connection. So how do you gather all this data offline? And when you think about this, it's quite common to need large standardized data sets. And in computer vision, it's quite common to need your images as well as your measurements and keep these organized. And finally, for field-based data collection, you might find yourself without an internet connection. So this problem isn't just related to muscles, it's actually quite generic. So how did we solve this? Well, we built an in-house multi-platform application, and this has support for Android, iOS, desktop, and web. It's certainly simplified the way we've collected our data, so let's dive into how we've approached this. So first off, we've made sure it can be tailored to any sort of data collection that you need. So we've done this by defining multiple data fields and media captures that you'll need for your process, and then we've allowed you to group these into step processes, which is then rendered out into a wizard format. So you can see on the slide there, we've got one of our AI collections, and then you've got one of the individual wizard steps there. So another thing we've found really important is to always consider your users and your environment that they're using the app in. So we've made sure to include a lot of guidance, like instructions, videos, dialogues within the app, so users know at any time what they need to do and what's going on. It's certainly made the app more accessible and usable by a wide range of users. So for us, this could range from muscle farmers who need big buttons out on the boat, or student volunteers helping us collect data. So once you have collected your data, we've made it easy to review and edit this. We've done this through a view where you can list all your samples, and then you can click and tap into them and view them in a detailed view, and you can customize this based on the collection that you are viewing. So finally, looking at offline, we've made sure that our app can save all our data locally on the phone, and then once you jump back into an internet connection, we can go and sync this back with our server. And once it's on the server, we can have this available for the ML pipelines that we're developing, and it's also available for other users on other devices. So finally, where are we looking at heading? We're looking to actually take advantage of the fact we are multi-platform and building out more of a web and desktop analytics solution. We are also looking at improving our exports, so you can take data right from the app and download that and put that straight into your machine learning pipelines. Finally, because this problem is quite generic and the challenges we're faced is quite generic, if you think you're facing similar problems or challenges and you think this technology sounds like it could be something that could help you, please come and talk with the Harvest Hub team. We'll be happy to talk with you. So thanks for listening, and come if you have any questions later on. Thank you.
Kia ora koutou katoa. I'm Yun Singh. I'm from the School of Computer Science. And I'm also the director of the Center of Machine Learning for Social Good at the School of Computer Science. I'm a co-director, actually. I'm a co-director with, where's Jill? Oh, Jill, and Daniel Wilson as well. I'm going to do a step change here. I'm going to do two things. First of all, I like to sort of talk a little bit about continual learning, because that's one of the research areas that my research lab works on. And continual learning or lifelong learning is a subfield of machine learning that focuses on challenging problems of incremental training models of stream data with the aim of accumulating knowledge over time. So recently, and I say recently, as in a couple of months ago, there was a paper or a survey that came out. And in that particular survey, they talked about when to do continual learning and examples of what things are in terms of continual learning. So continual learning is not just a choice. Continual learning is necessary and not just a tool that one would use. And that's what the survey says. And I, for one, truly believe this mantra. And so what I sort of want to do today is, first thing, I'm going to explain a little bit as using a case study, one case study from my group. And this, as Varvara pointed out, this was funded by TAIAO. So this is continual learning for anomaly detection for maritime trajectories. Jack, back there, has a poster outside. So I'm not going to go too much into this, but just an example of what continual learning can be used for anomaly detection in maritime vessels. So when we talk about anomaly detections in this particular area, we can talk about a couple of things: unexpected changes of speed or heading of a vessel trajectories, and it can signal a couple of things, whether it's oil spills, it can be that it's changing course because of a biosecurity risk, or it could be an illegal fishing activity out there. So there's various reasons why things change at sea. So there's a lot of open problems that we deal with. So previous work detecting anomalies predict when trajectories, what trajectories are, and comparing it with actual trajectories, which is fine. This is what we should do when we're actually detecting anomalies. But there is a significant difference in terms of what we classify as anomalous behaviors, because anomaly 2 years ago might not be an anomaly now. So things change over time, and how do we account for that? So that's one thing that we are trying to do. So we want to make sure that we're adapting when we need to and not adapting when we don't need to. So the first challenge is, how do we look at this and in terms of dynamically updating our models over time and avoiding forgetting? So this is the stability plasticity problem that we have. And second of all, how do we train a deep learning model to detect anomalies in a range of contexts on anomaly detection? So different contexts means there's different issues out there. So this is an example. On one of the graph on the left-hand side is changes in trajectories when you face things like whale sightings, and that's why ship changed course. And should that be counted as an anomaly? So there's different ways that we can deal with it, and I'm not going to go into too much detail, but these are some of the results. What I would say is the middle graph is actually quite interesting, because what we have seen here is that in real time, there is actually phishing that's happening, and other techniques also starts learning those techniques, that particular pattern that there's phishing, but ours doesn't, and it shouldn't have, because this was in a no phishing zone. So if we straight up apply techniques, it might adapt when it's not supposed to. So that's a simple example of that. I'm going to take 1 minute to showcase our center. So the Center of Machine Learning for Social Good is a transdisciplinary center. We have people from space, engineering, we have people from medical, and also from environments across and it's a range across different domains. So it's a catalyst to solve high-impact societal issues. And I'm just going to get one pager in terms of what we do. We do things in health, society, environment. So there's a range of projects that we actually sort of look at. I'm not going to talk about a whole lot of them. I'm going to pick one to talk about. At the moment, one of the very interesting ones that we are looking at, I'm not going to talk about people who knows me at the moment. I'm very passionate about stories, but I'm going to talk about our Voices. Our Voices is actually a program that was funded by MBIE. And what it does is it's partnered with Growing Up in New Zealand. And last year, and actually 2 years ago, we actually created an app. And that particular app allows us to collect information from various kids, and we're actually able to actually have a better understanding of what the kids feel like now. So that's us. Thank you so much.
Hi, I'm Bing. I'm going to talk about evolutionary machine learning approaches and applications. I'm from Victoria University of Wellington. I'm also from another center for data science and AI. I'm not a director. I'm a deputy director, or a director among Monjie Zhang and Steve. They are at the back as well. So you probably don't know what evolutionary machine learning means. So actually, we're working on a group of method called evolutionary computation as one of the 5 types of machine learning approaches. Of course, from the 5, everybody knows neural networks. So that's and evolutionary computation is one of the other 5. But we cannot do all of the 5s. I just want to focus on one as evolutionary machine learning today. We work on quite a wide range of topics within evolutionary machine learning. One of them being automatic or genetic programming, so which Dr. Chi Chen has talked about in the morning. The key strength of this type of approaches is, so basically, it doesn't need any assumption on the data, doesn't require any data distribution. It can automatically learn a model structure as well as a model coefficient. So it can create many different types of model, can be in various different structure. So another one and key area is the computer vision and image analysis, and probably also as well as speech video processing. From image classification, which identify different type of images, as well as for edge detection, salient object detection, object tracking, and also probably we should recently start with working on 3D reconstruction. So application areas also a lot of work on medical image analysis. Another area would be evolutionary transfer learning and multitasking. So when working on machine learning, we learn from data. We assume the data we get is sufficient, and we assume the data can actually represent the problem itself. But commonly, we actually don't have that high-quality data or enough data. So I really like this area because when you don't have enough data, and you can use transfer learning to transfer knowledge from other domains. So the knowledge can be the feature, the data points, a partial model, or any types. Another related topic is multitasking. So you not only solve multiple problems at the same time. I can see everybody here, majority of are doing multitasking. You listen to talks and you reply on emails. And this is something we should utilize for machine learning. And another one is multi-objective machine learning. We often need to have trade-off between different things, right? Model complexity and model accuracy. So what we want to do here is find the optimal trade-off at different data, at different points, so you can choose, make a decision based on your own preference or your requirement of the problem domain. And then the other one we do is feature selection or dimensionality reduction. You know, we not only have, we have a lot of data, but we don't want to have so many data. We want quality data. We want the data tell us the key information. So that can reduce the dimensionality or reduce the volume of the data via, you know, feature selection or feature extraction, feature construction. And our approach can basically use, you build a very simple model or feature constructor, a very simple, just use plus minus arithmetic operators and to transform the original low quality data to a very high quality data. So you can understand the problem much better. And a lot of evolution deep learning as well. And we see there's, you know, I don't really need to talk about how many deep learning model structure there are and different kind of deep neural networks, but that requires a lot of effort to design the model structure. What we have doing is we can automatically design the model structure for any problem, for any data we're given. Another one is called deep genetic programming that not only can give us a deep model, but tell us step by step how the model come up with a certain conclusion. As an example here, the last point is actually why we're doing evolution computation. So they basically don't need domain knowledge, but easily can incorporate domain knowledge. Does not make any assumptions, also can handle constraints very easily. Model structure and parameter learn at the same time, as well as multi-objective optimization interpretability. We're not only doing machine learning, we're doing general AI and machine learning, and many different areas of domain applications. And at the same time, we are seeking for collaborations. Yes, that's all. Thank you very much.
So if from the title you can see, it's more like apply the AI to solve some challenging problems. But before I talk about the specific topics, I like to talk about a little bit the reason we like to work on this specific direction. Basically, we have a mother project, is a catalyst seeding New Zealand and Japan one, and this is the reason we start working on this. I like to share with this project because basically it's ongoing, and this is last year. We're looking actually to grow this project bigger, like a catalyst strategic is our next goal. And if you look at the topic, it's basically the trustworthy and privacy preserving collaborative control technology for vehicle IoT. I like the short name is a trust PC for VIoT. So basically it's more from the trustworthy and privacy perspective to look at the technology, especially is for the purpose of driver safety. It's 2 years, and the last one, actually for the team members, is we have Kevin from University of Auckland here, and we have another Peter from my previous AOT, and also we have Ian Welch from Victoria University. But I have to say we are more engineers, we are more on the communication and working securities. But if you look at the challenge we want to solve, actually we do need help and support from you guys and from data science, from the AI. So the left side is we visit Japan, and the leader there is Professor Tsurimuga Wu in Tokyo, and another is the Japanese delegate come to Auckland last November. Because of the budget, actually support New Zealand researchers visit Japan every year once. And also Japan, they have their money to send their researchers come here. The research fund is not really big, it's small, but it's basically more like socialized touring. but we're looking for the bigger strategy for the next. This is our public statement. It's a little bit long, but the issue is, yes, we have a lot of AI data science used, but when you're using this in the vehicle perspective, especially if you want to give the drivers support to make decisions, actually the trustworthy and is very important. Oh, it's very quick. Okay, so basically it's very, very critical one. Okay, so anyway, we have different task groups, but basically the topic I want to talk about is on the safety issue, and then there is another big statement. But the point is, we see the generative AI is really great. It's like we have big hammer, it's very powerful, but we're looking for a nail we can actually put on. But especially for the driver safety, they need to make the real-time decisions. So this is the challenge part. Yeah, I think that can be a very complex, but if you think about a daily case, New Zealand, we have very not well-developed road. So for example, if you come out from your street, you want to turn right, actually you see the car actually come from your left-hand side. So I believe most of the time you are struggling, you look at left, you look at right, and if lucky, you find a gap, you go through. If not, probably you feel quite a struggle. So this actually is a user case we're thinking, because we actually quite depend on our eyes, and our eye has limitations in some situation like this one, and also in the bad weathers, and we want to see how the AI or the Internet of Things can help on this situation. Yes, definitely we have eyes on this camera surveillance, but the point is, how actually you feedback this information, especially in the black spot. Okay, for example, I cannot see the car there, but maybe you can install the surveillance camera on the opposite, they can see it, but how actually they can quickly send the information to the driver and let the driver make a decision, and this is the biggest challenge we want. Definitely you can say, you can send a video, with a video, but the video actually, when you're using wireless, the bandwidth is the limit. So it may be delayed, so the driver actually is really challenged. Okay, but anyway, so basically we are talking about like an eye, we want to extend the driver's eye using this Internet of Things, but the point again, how this information are sending back. Is video, is image, or is a message? And this is something like generative AI is help, especially this multiple community things. And we see a paper talking about you get a picture, and then you actually get the abstract of word, and then you send a word, and then in the local, actually they can generate the picture back. It looks like a good idea, but is this really working in the real time? Because driver actually really need accurate and instant message to make a decision. Otherwise, if the message is wrong, the driver is got accident. So this is something probably I leave at the end, is rather we find a solution, we actually pose a question. Because we are networking communication guys, but we want to see if AI can help to make the communication efficient and accurate. And this is the trade-off problems. Thank you.
Kira, I'm Nick Lim from Waikato, and I'm a researcher attached to the Tile project. So today we're just sharing some of the learnings that we had from exploiting what we call the explanations of image classification examples. All right, so this was the initial motivation for the research. So some of you that have done labeling will probably know the pain of labeling what we call images. Usually it takes about 4 seconds or so to do a classification label, about 40 seconds, 20 to 40 seconds to draw a bounding box for object detection, and it takes about several minutes just to do a segmentation, to map up the segmentations of examples. And one of the ideas behind this is that whether we can exploit the explanations from the classification models to basically uplift the labels to basically try to localize the object, or even possibly get the segmentations of those objects. So fortunately, there has been quite a lot of research in understanding explanations of image classifications. So on the top example, we have some what we call visualizations of the attention head from vision transformers. So we can actually look at the outline, you can see the bird in the image, or the toothbrush. The toothbrush is in the image of the teddy bear, the toothbrush. Otherwise, you can also use traditional methods such as layer relevance propagation or saliency maps, or some of you are maybe really familiar with CAM-based visualization, classification modules. So these are some of the learnings that we have from using classification example, using the CAM examinations to uplift to the object detections. So one of the things that we found is that it's usually quite helpful to provide the classification the classification model with multiple views of the image, and that does give it a more consistent and more robust bounding blocks of the object. So the left of this is the image with just one single view of the person, and on the right is with it's basically you can think of it as an augmented explanation for that's done over multiple views, which include flips and rotations. And the other thing that we'll also notice that in many of the pre-trained models, they do tend to struggle in what we call background classes. So if, for example, you look at the bottom right, the sofa, it tends to focus on, not really a sofa, it feels quite badly there. So there is something that you might need to keep in consideration, that in classification of background images. Look at the explanation for this classification. It might not actually pick up the actual object. It might be actually be using some proxy features in order to generate the explanations. So there's something that we should do. So one application that we tried to apply this thing. So we're talking about the mussel industry for quite a bit. So this was an application that we did for the Ohiva Harbour, where we tried to use this method to identify sea stars in the images. Next is how can we uplift from detection to segmentation. So many of you have, some of you have been aware of the auto-segmenting methods such as segment anything. And yeah, so this takes a bit of finessing. I won't go into details on it, but one key learning that we have is that some of these auto-segmenters, they tend to miss the forest for the trees, literally, in the sense that it picks up stands of trees rather than forest. So that takes a bit of finessing in order to get it to do well. We have some extra details of this with my colleague there, Dr. Ananya, with his poster in poster number 12. So sorry to put it on the table. So for those who know Cantonese, you know what that expression means. All right, yeah, and finally, we can also go from explainative to better classification. So this is an ongoing work that we are exploring. So the work just currently found some preliminary results, and they are really helpful. So one of our previous works have shown that there is a correlation between the quality of the explanations and the accuracy of the classification. So if we are able to improve, focus the model's explanation onto what the true explanations are, it does help with the classification accuracies. Right, thank you everyone.
Good afternoon, everyone. I'm Mohammad Noor Zifar. I'm the research fellow at University of Auckland, and also the academic member at NZSEG, the college. Today, I would like to talk about our research, which is related to the kids' eye health and diagnostic, especially for the kids who are suffering from amblyopia or lazy eyes. Usually kids with 3-4 years old, they need to do some eye checking. If this type of eye checking happen during this age, can be detected these amblyopia at early stages. It should be really helpful for the treatment. But the challenge is the kids, usually they are not engaging or talking to the parents because they don't have experience for the good vision, the good quality of their vision. By the way, as a researcher, we try to help this or tackle this issue with using the eye tracker. But it's another challenge when you're gonna use the eye tracker as a glasses for them, for the kids. Usually they would like to wear something really comfortable. But I will not talk about this project. I will back to the technology that we use to, for this issue. Okay, in the past, they usually use some rolling pattern. They call it on the left side, you can see. But nowadays, we have some other tools to be able to use for the kids around 3-4 years old. But still, clinicians are struggling to detect this issue at the early stages. That's why we would like to have something like fancy glasses. It's quite expensive. It's come from the Pupil Labs company in Germany. But we are developing our own POC to be able to be really reasonable and cheap, but is on the way. This eye tracking can be helpful because the data come from the eye movement. The issue from the amblyopia or lazy eyes is not a problem from your eyes. It's come from your brain. Is the issue come from the brain? The organ, it works well, the eyes, but the brain is not developed well. That's why we should use the new techniques that kids doesn't need to talk, doesn't need to do anything. Nowadays, we try to engage the children with developing the game. It's a kind of the simple game to be able to joyful for them. At the end of the day, we have this kind of result as a collected data. As you can see, this QR code is the pattern. If you scan it, you can see the drifting dot. They call it a stimulus. This drifting dot will make the pattern through your eye movement. They call it optokinetic response. This response is involuntary response. Your brain will generate when you can see the pattern is movement. As you can see through this video, this little shaking or response will happen because of the kid is having, watching the screen, that the screen does have the pattern that we want, like drifting dot. By the way, we tried different techniques. One of the techniques that we use is based on the machine learning, using the video data to detect this really subtle event, the OKN pattern. This pattern should be really close with other type of eye movement. That's why it's quite complicated to be able to distinguish between the OKN response and other eye movement that is kind of the voluntary one. We have done the data cleaning, and also we try to chop the video with the hop lens and overlap with each other. And one of the techniques that we use is a kind of the mask autoencoder. This model will help us a lot to be able to improve the quality. And the video is chopped based on the really short time. It means 1.25 seconds, because this pattern is quite small. Is the challenge, and they have the overlap. We got a good result so far. Of course, the data needs to be generalized. We need to do more tuning, but the current result for the mean average precision is around 86% for the collected data set. And also, we have the confusion matrix for the test data set, as we can see. And also, we are open for collaboration. Please send an email to me or my line manager, Dr. Jason Terfano. Thank you very much.
Yes, I'm Albert Bifet, Director of the AI Institute at University of Waikato, and today I'm very happy to talk about Green AI and the Tayao project. So why Green AI in New Zealand? Well, if you talk with people overseas, they always think that one of the main values or characteristics of New Zealand is the greenness, right? So we are very well known for that. And what is green AI? Well, green AI is the combination of working on environmental problems, but also at the same time doing that in a way that we don't use too much energy. So yeah, I'd like to talk about these two things. So the Tayao project is a big project of 7 years with 4 universities, the University of Waikato, University of Auckland, Canterbury, and Victoria University of Wellington, and Becca and Med Service. And basically what we want to do is to help environmental scientists to benefit from data science and AI. So the best thing of the project is the team. So you have seen also the talks before from Varvara from Canterbury, Yunsing from Auckland, Nick from Waikato, and we have also Bernard from Waikato. I don't want to miss anyone, but we have also Guillermo and Annie. We have Phil, so many, many people. So the best thing of the project is the people. We have many outcomes. So one is this community website. The idea is that we want people to collaborate. So the idea is that we host data sets, we host notebooks, discussions, so the people have a place where they can go and meet and discuss. We have several open source tools. So one is this species identifier. So this is something that runs on the mobile. So you can go to the forest, it's not using the cloud, and you take a picture and you get, what's the species, you have the top 5 prediction, you have the explainable AI, and now you have also some Wikipedia information. So this is a project also done with Varvara from Canterbury. We have this collaboration with NVIDIA. The idea was to build this accelerated Weka. So the idea was to have Weka that can use GPUs. So that was a project done with them. And what the program is, it's fundamental. So we work on building new algorithms for machine learning, new tools, but also at the same time we are applied. So we have seen also the applications of Varvara and Nick, Yunsing. So we have been working on many things. One of the main projects is this flood forecasting model with the Waikato Regional Council, where we try to see if we can predict floods. There is also this project of river proof from space, where I already mentioned the Aotearoa species classifier. Also this application from Varvara on how to use graph neural networks for these ocean temperature extreme events. The main idea is basically try to use these deep learning tools, these machine learning tools to benefit from this, right? So instead of the scientists having to go to the lakes to measure, so just using satellite images and being able to do that in a much cheaper way, right? So we have this detecting toxic algae from the space. This is a project from Yunsing. This seagrass mapping from remote sensing, the one that Varvara mentioned about foil wind events in the Rift Valleys, and the invasive sea stars in NIWA that Nick mentioned. So that's the Tayao project. So what is green AI? So green AI is trying to do AI in the most efficient way. So what is the most efficient way? Is just do one pass over the data. Just not store the data, do only one pass, and be very, very efficient. So that means using approximate algorithms. So instead, if the exact solution is going to take 1 week, if we can have an approximate solution with only 1% of error in minutes, we prefer that. And for that, stream machine learning is perfect because that's the goal. The goal is we don't store the data, we do only one pass, we are very, very efficient in terms of time and memory, and also at the same time we are adaptive. So we have already published this book on machine learning for data streams with practical examples in MOA. So MOA is an open source software in Java. We have now a version that is in Python. It's called River. This is in collaboration with French researchers. And the idea is to have something that you can use on Jupyter notebooks. So that's all. We are open to collaboration. So please, if you are interested in collaborating with us, let's keep in touch. Thank you.